Hi, I have done yesterday the complete reverse engineering of this board. This one. It took me the entire day. As I suspected, on this board there are two synchro outputs, but not only. There is also one AC output, which is actually an ARINC 565 interface. This output delivers an AC signal which can be in phase or out of phase regarding the reference AC voltage. And there is also a DC output which would be conform to ARINC 575. As I said, I first studied this board, which is the magnetics module. For that purpose, I have removed these two transformers, and I have found that effectively the turn ratios between these two transformers are exactly square root of 3 divided by 2. So these are effectively Scott transformers. One has only one winding, and the second one has a middle point, but there is also another tap here. We'll see later why. And there is another small transformer, which is this one here, and as I suspected, this transformer is used effectively for the AC reference of the synchro. So there is a primary side which is connected to two pins of the rear connector, and the output voltage reference is here. This voltage is fed to the output board. There is also another winding with a middle point here, which is connected to these diodes. These diodes actually are connected also to the rear connector, as you can see. So we have the connections for the middle point and two other connections for the output voltage, the positive one and the negative one. So I don't know the purpose of these diodes. Anyway, they are not used inside the device itself. On this page, there are the representations of all parts. It is important to draw, for example, for an op-amp, the internal symbols. It is also the case, for example, for the resistor arrays here. And if it is a complex part, like a DAC, I write the definition of the pins. And it is the same also, for example, for a gate. If you have an IC with different gates, it is important to draw the symbols of the gate. This will help for the reverse engineering. And it is the same for the transistors. It is important to determine the type of transistor, if it is a PNP, NPN, MOSFET, etc., and to draw the exact symbol. When all the parts are placed on this page, then you have to draw the interconnections. I use different colors for that, as you can see. And it is also important when you have a transformer to do something like that. So you need to desolder the transformer and to measure the DCR of all windings. It is what I have done first here. So this permits to determine the various windings that can be isolated or not. So now let's see the final schematics. This one is less complicated. It concerns the DC output, which is here, connected to the pin H1 on the rear connector. The output voltage of this op-amp is a unipolar signal. In order to have a bipolar operation, it is something classic. You add, thanks to this op-amp, a part of the reference voltage, which is here. Actually, it is half the scale, as you can see. So we have 20K, and here we have 10K. So these resistors are actually inside the resistor array. So this permits to have a matching between these resistors. The absolute value is not important, but what is important is the ratio between these two values here. At this point, we have a bipolar voltage from minus something to plus something, which depends on the 12 bits binary code, which is fed to the DAC. For the mid-scale data, we have 0 volt at the output of this op-amp. Then the voltage is attenuated using these two resistors and is fed to this buffer. As you can see, we have a protective resistor here, so it permits to have a short circuit. The second page concerns the ARINC 565 output, that is to say an AC voltage. It is a little bit more complicated, as you can see, but we can recognize on the top of the circuit more or less the same circuit than the DC output. So we have a DAC. Instead of using a DC reference, the reference voltage is an AC signal, which is the output of this differential amplifier. The input of the differential amplifier is connected to two pins of the rear connector, G2 and G1 here. So this signal is used as a reference voltage of the DAC. And in order to have also 0 volt for the mid-scale, there is these two resistors which permits to add an offset at the output. So when there is a mid-scale data which is fed to the DAC, we have 0 volt at this output. So the output of the op-amp is fed to this push-pull buffer here. This is actually this push-pull here. And the output of this buffer is fed to the transformer, which is actually the transformer which is in the middle of this board, this one here. The rest of the circuit is the measurement of the AC voltage which is on the primary side of the transformer here, and also the measurement of the reference voltage. So for that purpose there is this single wave rectifying here using this diode, this capacitor and this leakage resistor here. It is the same for the primary voltage, and these two DC voltages are fed to this ADC, which is the ADC 0832. This is this part here. So I don't know the exact purpose of this circuit, maybe for some diagnostic or something like that. And there is also on the bottom of this page another circuit here. So these two AC voltages are fed to these two comparators. The threshold is close to the ground because we have here a resistor of 2.7 kilo ohms, and the positive feedback which is created by this 10 meg resistor. This creates a small hysteresis, but the voltage is very close to zero. At the output of these two comparators we have a square wave. Depending on the phase, these two signals will be in phase or out of phase. So there is a phase comparison using this exclusive OR gate, and at the output we will have a high level if these two signals are out of phase, and a low level if they are in phase. So this is a detection actually of the sign or the phase, if you want, of the output regarding the voltage reference. So I don't know the purpose of this circuit. The phase depends on the data fed to the DAC. It is maybe used for auto test or for some diagnostic, I don't know. The last circuit is a digital to synchro converter, which is on this last page. The goal is to have first, as I said in my previous video, a resolver system. The goal is to have on these two outputs, this one and this one here, two AC signals in phase at 400 Hz, but with amplitudes depending on the sine and the cosine of the angle. The angle is the position of the shaft of the synchro you want to set. After the resolver system, we have the Scott transformers, as we have seen in my previous video. So there is one with only one winding, and the second one with a middle point here. So it is not complicated. It is more or less identical to the ARINC 565 circuit, which generates an AC voltage. We have, on this case, a reference voltage which comes from this transformer. It is this small transformer. This reference voltage is fed to the reference voltage of the DAC. The DACs are of course 4-quadrant multiplying DAC. It is also the case for the previous systems. So you can see that we have effectively this resistor of 10K, and the first one here is 5K. So this permits to have at mid-scale here 0 volt at the output. Following this op-amp, we find this push-pull circuit here with these two complementary transistors. They are actually BD139 and BD140, and the feedback, of course, is connected at the output of the buffer, and the output of each buffer is fed to the primary side of the Scott transformers, this one and this one. Normally, when we want to drive a synchro, we just need only one center tap here. If we use a synchro, this signal should be connected to another signal of the second transformer, but as you can see, the connection is not present inside the instrument, and we can see that we have also an intermediate point here. So I have measured the turn ratios of this transformer, and I have found that effectively, if we consider the external terminals of this transformer, we have exactly a ratio of square root of 3 divided by 2. The turn ratio is 1.75. If we consider these two terminals here, the second one is 1.52. If you calculate the ratio, you will find something which is close to 0.87, something like that. But I have measured also the turn ratio considering the terminals B30 and A28, which is an intermediate point, and I have found that in that case, the turn ratio is exactly 1.52, which is the ratio of the first transformer. Obviously, this thing is done in order to drive either a synchro, either a resolver. If you use the terminals B30 and A28 for this transformer, and B29 and B31 for this one, you can connect these two outputs to a resolver, and this will work also. So it is possible to connect a resolver or a synchro to this system. So this is for one channel. The second one is identical to this one. So we have another reference voltage and two other Scott transformers. So all the 6 stacks are the same. They work with an SPI bus. So there is one common bus on this instrument, and the selection of the DAC is done using this decoder, which is a classic HC138, which generates actually 8 outputs. 6 are used for the DACs. Another one is used for the ADC, and there is another one which is used actually for a shift register. I didn't speak about that, it's just a detail. This thing, this shift register, I will make a zoom on this thing. So this permits to read actually 8 inputs. One input here, H, corresponds to the phase of the AC signal. We have seen it is the output of this exclusive OR gate here after a small filtering. We have also 2 inputs which are connected to the rear connector. So it is possible to configure something by placing a short circuit on the rear connector. And there are also these 4 jumpers which are placed here, as you can see. So this permits to have a configuration of this board. So I don't know exactly the purpose of this thing. What I would like to do is to connect this board to a small microcontroller board in order to test this system. This could be interesting, and I think it's not complicated. I just need to provide an SPI bus and also to generate a sine and a cosine value which will be fed into the DAC, and normally this should work. We will see next time. Thanks for watching and see you next time. Bye bye.